Welcome to this explainer. Today, we're diving into a foundational technique used in literally every bioanalytical lab worldwide and exploring some hard data that suggests it might just be time for a massive upgrade. We're talking about ELISA antibody optimization. For decades, we scientists have relied on one specific, highly traditional method to find that perfect signal-to-noise ratio. But as our experiments get more and more complex, that old-school approach is probably holding us back. So we're going to explore how upgrading from classic checkerboard titrations to a modern multifactorial approach can completely transform and accelerate your entire assay development process. Is your checkerboard titration wasting precious reagents? I mean, think about it for a second. If you work at the bench, the checkerboard titration is probably one of the very first things you were ever trained to do. It feels safe, it's reliable, and it's super familiar. But what if the very tool you trust the most to optimize your assays is actually costing your lab time, money, and accuracy? Today, we're unpacking exactly why this happens, the hidden limitations of the tools we use every single day, and most importantly, what you can do to fix it. The classic checkerboard approach. It's visual, it's intuitive, but ultimately, it's limited. Let's move right into the hidden flaws of checkerboards and why this classic method is holding your assay back. We all love the checkerboard, right? You dilute your capture and detection antibodies across a standard 96-well plate to just visually eyeball that sweet spot. But actually, this is a textbook example of OFAT, one factor at a time testing. It's a method where you're testing variables sequentially. Even though you are technically testing two variables, you find those optimal antibody concentrations on the plate, and then you lock them in. After that, you move on to test other factors, like your blocking buffer composition or your wash steps, completely in isolation. By locking in those antibody concentrations so early in the game, you totally miss the critical synergistic effects between all these different assay conditions. And this is a major problem, because biological systems are incredibly interactive. Doing things this way completely fails to efficiently model those interactions. It's like you're only getting a flat 2D slice of a highly complex 3D system. For instance, maybe a high concentration of capture antibody actually requires a much more stringent wash step to prevent a high background signal. You wouldn't see that on a classic checkerboard. Plus, this method is highly resource-intensive and time-consuming. Because if your first checkerboard doesn't give you a good signal-to-noise ratio, well, you have to start all over with a brand new range of concentrations, wasting precious, expensive reagents and completely derailing their timeline. Real quick, before we look at a multifactorial alternative to this 2D problem, are you enjoying the science and the structure of this explainer? If you are, make sure to like, subscribe, and comment below with your absolute toughest ELISA challenge. We love hearing from fellow bench scientists, and your biggest headache might just be the focus of our next explainer. Okay, let's get back to the solution. Which brings us to the DOE advantage, a true multifactorial game changer. Let's contrast these two approaches directly. The traditional checkerboard is stuck in a 2D matrix. It finds a local optimum, and it forces you to work sequentially. But design of experiments, or DOE, is an advanced statistical approach that creates a multidimensional response surface. It finds the global optimum, and it does it simultaneously. Instead of optimizing your antibody concentration in a vacuum, DOE lets you design a single experiment that tests your capture antibody, detection antibody, blocking buffer type, and incubation time all at exactly the same time. Because it looks at everything together, it ensures you find the true global optimum across the entire landscape, rather than settling for some fragile local optimum that completely falls apart the second you change a buffer. To put the power of this into perspective, let's talk about the number 15. Mathematical models from our source material revealed a really powerful example. They found that you could achieve the exact same assay sensitivity using a significantly lower and much cheaper concentration of detection antibody. How? Simply by extending the incubation time by exactly 15 minutes. These kinds of hidden cost-saving insights are literally impossible to glean from a standard 2D checkerboard, simply because they depend entirely on how those two variables interact with each other. There is a quote here that perfectly sums up the sheer efficiency and speed of this mathematical modeling approach. A well-designed fractional factorial can provide more actionable data in a single run than weeks of sequential OFAT testing. Now sure, DOE might require a slightly more complex initial setup mathematically, but it drastically reduces the overall number of experiments you actually have to run at the bench. It's really about working smarter, letting the statistics do the heavy lifting, and getting a rock-solid assay in a fraction of the time. So, transitioning to DOE workflows, moving from sequential to simultaneous testing. Now, I know transitioning to this mindset sounds a little daunting, but the workflow is actually a highly logical and actionable progression. Let's walk through the 4 steps to implement DOE in your lab. Step 1, define your goal. Are you trying to maximize signal to noise, improve sensitivity, or minimize background? You need to clearly define your critical quality attributes, or CQAs. Step 2. Select your factors. You'll obviously include your capture and detection antibodies, but you'll also want to add 2 to 3 other suspected critical factors, like a blocker or incubation time. Step 3. Choose a design. If you're testing 4 to 5 factors, setting up a fractional factorial design or a custom definitive screening design works incredibly well. And finally, step 4. Execute and analyze. You just run the plate, punch the data into your statistical software, and let it map out that response surface to find the absolute optimal combination of all those factors at once. You might be wondering, can I just use Excel for this? Well, honestly, standard spreadsheets simply won't cut it for robust response surface visualization. People do often ask if they can still use a checkerboard at all. And the answer is yes, actually. A very broad, sparse checkerboard can still be useful as a quick range-finding experiment. But for true robust modeling, you need dedicated statistical software. The source recommends industry heavyweights like JMP, Design Expert, or Minitab to handle the complex math running behind your assay optimization.
Accelerating assay development, building robust assays, and unlocking major cost savings. To wrap this all up, moving away from checkerboard titrations and embracing design of experiments is arguably the single most impactful change any bioanalytical lab can make. By understanding how variables truly interact, you clear out those massive development bottlenecks, you build much more robust assays, and you achieve some pretty serious cost savings on those incredibly expensive reagents. So, are you going to stay stuck in 2D, or is it time to upgrade your lab? If your team is constantly banging their heads against the wall, struggling with assay sensitivity, frustrating backgrounds, or endless development cycles, you do not have to keep relying on outdated methods. Subscribe to Assay Optimization Lab to learn more about applying advanced DOE methodologies to your complex immunoassays. Thank you so much for joining me for this explainer, and I hope this helps you optimize your very next big experiment.